Okay, so the next problem in the lead code we are solving is triangle. Okay, so why it is called here we have given the two-dimensional array. Okay, and it consists of an integers. Why do we call it as a triangle? Because it can be represented in this format. Okay, so the first array will contain one element, and the second array two element, third array three element. So it can be represented this way. Okay, and here we are asked to traverse from top to bottom. Okay, here they are represented in a triangle format, right? We'll need to traverse from top to bottom. Okay, and we need to find out a minimum path sum. Okay, but the given condition here is let's say that you are starting from here. Okay, you are starting from here. You are going to let's say that these are separate array, right? This is a first array, second array, third array, fourth array. Okay, currently you are here. Okay, currently we are here 0. You are at in this first array you are at a 0th index. So in the next array you can you can go to 0th or 0 plus 1th index. Okay, so basically here, right here, the index is 1. Index is 1 here. So in the next array you can go to 1 or 1 plus 2, 1 plus 1, right? So basically it will, you can go here or here. Okay, so to let me just explain this further. Okay, this is the given condition. Okay, like how to traverse and everything. So basically you will be starting from here. You will be start from here, and either you can go to here or here if you draw it in this format, right? Again, if you come here, you can either go here or here, I or I plus 1. The same will be applicable to everything. Okay, so you can take here also. You can go either traversal here or here. You are not supposed to traverse in this way. Okay, now let's try to see like how we can approach this problem in an efficient way. Okay. Okay, as we just saw, right? Like, I mean, it was nothing but a tree data structure that we are getting, right? This is how, like, I mean, we can represent the whatever that we got, right? We can represent it in this format, and it actually looks like a tree, but with a small modification that, like, I mean, their nodes are interconnected here. Okay, so now let's say that what is the problem here? The problem here is we are starting from here, and we need to traverse to the end, like which will be the shortest path. Okay, so I can traverse in this direction, or I can there are n number of ways, right? We can solve this via recursion and to get an answer here, right? But we need to solve it efficiently. Let's go into see do some analysis here. Okay, so let's say that I'm going to pick this node for example. Okay, so if I take this path, like what are the number of ways I can reach to this, right? Like, I mean, if I am going through this path, let's say I might have came from here, or I might have came from here, right? Like, I mean, there are two paths that are going through this common path actually, right? So let's say that this is only two paths. Okay, let's say that we have some other node called x here, some node here. Okay, so that will also that might also come here. So now what it will look, again there is one more node, and again this might pass through this. Okay, so what we can notice here is like there can be n number of combinations. Okay, that might be passing through this, right? Every time calculating the sum for it, right? Like every time I need to calculate 6 plus 9, 6 plus 9, 6 plus 9, right? So it's like a duplicate operation we are doing, right? So whenever there is a duplicate paths or duplicate operations we are doing, obviously it will increase the time complexity here. And also we should, as much as possible, we should always actually try to avoid the duplicate operations. Okay, so as we're talking about duplicate operations, so it means that like if I want to avoid these duplicates, so I need to store it somewhere, right? So I can reuse it. Like I will store this somewhere. I will say it as a cache. Okay, so I will store it in the cache. So next time whenever we hit 6, right, I can directly pick that value. Correct, I can directly read the value from the cache, and I can proceed further. So if the path comes like this, I will not proceed for, okay, 6 will already have that value stored. I will read it. I don't actually proceed further. In this way, we can save multiple operation, right? Like whatever the path that we are taking, whatever the different paths, ultimately we'll stop here. Ultimately we'll stop here, and I mean we'll not proceed with the same calculation again and again. Okay, this is the small tree structure view. Okay, but if the tree gets bigger, right, this will help us a lot. Actually, let's say that if the tree is of this much size, right, like there are nodes can be coming from the different directions, and every time we're doing the calculation won't be ideal. Correct, so that's why what we are going to do here is caching. Okay, whenever we are talking about caching, it's nothing but a DP problem we are trying to solve, right? Like any backtracking problem will have a problem with like performing the same action and again. So using adding some cache mechanism to it, we can improve the performance of it. So that's what is called as a dynamic programming here. Okay, so now let's see that how we can solve this problem. Okay, let me clear this out first. Okay, now we got to know that when we start traversing from here, right? So this is some duplicate. Okay, so it means that these nodes are depending on this one, correct? The top nodes are depending on the bottom node values. Okay, here we just took an example of 6. You see, it's the same case for any other nodes that you see here. Okay, so what we'll do is we'll try to find out a path sum for this one first. Okay, we'll try to save it for this one and we'll update it. Okay, we'll update this value so that upper nodes, whatever present right here, right, they can directly read the values from there. Okay, so it is like there are two persons here. Okay, there are multiple persons here, and instead of you yourself going to the end and checking the distance, we can simply ask this guy, like, I mean, what was the distance that is left to cover or something like that, right? This guy responds. You will just have to consider that and increase count it for the path sum. Okay, so let's say that now what are we going to do? Now we know that these values are dependent on this, so we should get the value for this first, right? So now let's calculate the path sum for this one. So if I calculate a path sum for this one, what it would be? 6 plus 9. Like, I mean, we need to kind of also we need to find it efficiently, right? So let's say that if I for currently already we have a 6 here and we need to take a 9 here. 6 plus 9 will be, this will constitute to 15, correct? And 6 plus 10 is 16, right? Which is minimum here. We need to find a minimum, right? So this will be give you the minimum path. So that's why I will erase this and put the 15 here, right? So if anyone coming to this path, right, anyone, let's say that if either this way or this way, anyway, right, I will just tell them that the path sum, the next efficient path sum is 15. Okay, so they can add them to the add their values to them, add their values to their sum. Okay, yeah. So this is what we are trying to do. Okay, like for any we'll do it this way. Okay, we know that why we are doing it, because these values are dependent on this one. So we need to solve this first to get to the top, right? So we'll start from, so now we'll start from the bottom and we'll start solving. Okay, here, right here, do you see anything here? There is nothing, so nothing but minimum is nothing but equal to 0. So whatever that is left here, right, for the bottom trees, it is always the same. There is nothing left, right? That will be the minimum values. 8, 9, 10, 11 will remain as it is, but from here the next level we'll have to start um, picking the minimum value, which is minimum here 10 or 11. Minimum is 10, so I'm going to add it to this one. So plus 10 will be equal to 17. Okay, similarly here also, which is minimum here 8. 8 plus 5 is 13. I will going to do this. So now I'm updating the same tree with the new values now. Okay, so this is 13 and this will be 15, this will be the 17. So whenever this guy comes, okay, like 3 will talk to this guy, he will not talk to 8 or 9. You will directly read this value and you will add this value to himself. So here if you check so ultimately now when he comes here, right, he will also apply the same logic. Here is 13, here is 15, which is minimum. 13 is minimum. So what he will do is 13 plus 3 will just update himself to 16 now. Okay, I will update him to 16. And here also 4, which is minimum. 15 or 17, 15 is minimum. So he will pick this path. Actually it means that it will pick this path. 15 plus 4 is 19. Okay, 19. And also finally this guy also will do the same thing, which is minimum. This is minimum, so you will take 16 in this path and 16 plus 2 will be the 18. Okay, so this is how it looks. Okay, so ultimately one second. Okay, okay. I was thinking, like, I mean, I was trying to check with this problem. Like, I mean, answer should be 11. But this is correct, actually. Whatever we solved is correct, because this is 9 here. This is not 1. Here in this problem, it was given 1 here. Okay. Okay, let it be, actually. But whatever we are solving is correct. Okay. So basically, so this will be the efficient path. So what did we do here? Let me draw the path now. Okay. So we took this path, correct? We went which was the minimum. We took this path. Okay, now here, which was the minimum? This was the minimum, so we took this path. So here again, which was this path? This is the minimum. So here the shortest path is this way. This is the traversal shortest path. If you take any other path, it will give you the more than this value. The answer will be the 18. Okay, I hope this is clear. Like, I mean, how did we come into this solution, right? So how it is, like, why are we solving from bottom? Why are we not solving from the top? Those things. Okay, let's quickly recap. Let's say what we are like how we came here, right? So basically we have been given the triangle, and we know that how to traverse and everything. And we were able to notice that it's a tree problem, and also, like, I mean, there are duplicate, like, I mean, we are doing a part traversal and there is a duplicate in it. Like, I mean, we are going to traverse through it again and again. So what we did is, we thought of storing some value. As we're repeating the same operation and again, we thought we can enhance the time complexity by storing its operation so that I can reuse it later, right? So once we got to know that we need to store it, it's a typical dynamic programming problem. Okay, so now So now we know that top is dependent on the bottom, so that's why we started solving from the bottom. Let's say that if it's in some cases bottom might be dependent on top, in that case we'll might have to restructure the tree and start solving from the other way around. Okay, so this is the problem. So we understood that this is what we need the bottom values to be solved first, so we are iterating from bottom to top now. So every time we do it, we'll check the next index, basically I and I plus 1. If it is there, we'll calculate, or we'll calculate, like for the last node we can skip altogether because there will be no child nodes. For here we will compare, we'll get the values from this one with this one, whichever is minimum we'll add to the current value to increase the, like, calculating the sum. In this way we'll be doing it efficiently, like we won't be doing the same operation twice. We solve this tree, right? Like, I mean, we got an answer here. Did we duplicate any task? No, right? So it will be the efficient way, and it's a dynamic problem. Let's say, let me quickly show you the code actually. So first thing is we need to know, like, the dimensions of it, right? So that's why how many arrays are there, we'll get it here. Okay, you can just read it actually, like if the things, any things are not clear, I just briefed it down here. Okay, so basically here we are going to iterate through the triangle, and it should be reverse way, right? We need to start from the last array first, and then this one, then this one. Okay, and here also we need to skip the last error, right? We don't have to analyze it. So if you want to handle it, like if you want to go it anyway, so you can have to put m minus 1. And also you need to handle the case here, like overflow cases you need to handle, because we are trying to read the next index array, right? Next array elements that will error out, so you need to be careful there. Okay, so I'm using m minus 2 so that I skipped all together because I don't need to update it here. Actually, usually in dpi arrays, like, I mean, problem, we build a new dp array, you can solve it in that way also. But here I'm currently in play, I'm doing in place update. Okay, so left value, and what we're currently doing here is we'll be coming from the bottom array, and for each of the array we'll be checking for the left value and the right value. Okay, once we get it, whichever is the minimum, right, we'll be adding it to the current one, updating it. It's a plus is equal to, it's not just an update, it's a plus is equal to, so we are taking the sum of it and updating it here. Okay, so ultimately, like, after solving the problem, whatever that is comes in the top will be the answer for you. Okay, yeah, that is it. Thanks.